Why be normal? Well, why not? But that's not really a good enough reason. Let me thank you for being here today and agreeing to listen to me for a little while. I'd like to hear what you think about this after we're done, so feel free to contact me by phone or email anytime. And a friend of mine asked me this question the other day, and I just wanted to pass it along to you. If you know something about distribution models, and many of you who use at-risk know something about a few, I wonder which distribution, if you were trapped on a desert island, which distribution model, if you could only have one, which one would you have? Anyway, think about that for just a couple minutes. Here's the outline of my talk today. I'm going to start out talking about why use distribution models. Can we get along without them? Can we, are there reasons why we should not use them or should use them? What's the purpose of having them? And then I'll go over 4 different graphs that people use for selecting distribution models and talk about what their features and pluses and minuses are and tell you which ones I think are best. Then we'll talk about goodness of fit tests and a few popular ones, and again, what's good and bad about them and which ones I think are best. Then we'll talk about how to fit continuous distribution models using at-risk and how to fit discrete distribution models, and we'll close with some fitting examples. Or they could be examples of fitting, I'm not sure yet. That's the outline. Let's start with, why do we even need these things called distribution models? Well, there are 4 general things that we do with distribution models, and hopefully they make life better, easier, faster, more efficient, whatever it is. Let me see if I can not mess with that, actually. Just ignore the last 5 seconds. Good. Let's talk about what do we do with distribution models. Well, the first thing that people do with them is they use them to estimate how a population behaves based upon the behavior of a sample. And we might do this by deciding which distribution model fits best and then estimating the parameters of that distribution and estimating confidence intervals for those parameters. Many of you might have calculated confidence intervals for the mean and standard deviation, and typically we do this assuming a normal distribution, and that assumption allows us to do that and to get reasonably nice, tight, well-defined confidence intervals. But is that really best or most appropriate? Another use is prediction. We often want to be able to predict the probability of future values of some random process, and if we have a distribution model, that makes it quite easy to do these predictions. Now, if you're a user of at-risk software, whose manufacturer is sponsoring this webinar, then you're probably familiar with Monte Carlo analysis, which allows you to simulate a wide variety of systems. And a key aspect of Monte Carlo analysis is that we need random inputs. The easiest way to specify random inputs to your simulation is by specifying a distribution model. Finally, communication. Distribution models give us a set of simple words to describe really a complex concept. If I say a certain thing is normally distributed or exponentially distributed or Weibull or something like that, that conveys a fairly complex concept in a couple of words. Without those models, it would be more difficult to communicate that. Let's look at a picture and see what I mean. Now, you don't have to use distribution models. After all, these models have only been around for a few hundred years, and people tell me that many people did survive their entire life without using distribution models. I find that slightly incredible, but I think it's possible. So let's consider that that is an option. And maybe in some cases, it's better not to use a distribution model. You could, of course, just use the data you have. On the left of this slide, I have a histogram. That's just the data, no models. On the right is a distribution model I've fit to that data. And I can use that distribution model for any of the things I just talked about. Or I could just use the data for any of those things I just talked about. Which course is better? The distribution models make life better if you have the correct distribution model. Let's look at estimation. I can calculate confidence intervals for things like means of standard deviation, assuming a distribution model or not assuming a distribution model. But with the benefit of a distribution model, those confidence intervals are narrower. This means that our estimates are more precise. They're closer to what we believe to be the truth. However, if the distribution model is not the right one, then they could be quite far from the truth, and that's a risk we take. If we're doing prediction, then a distribution model allows us to extrapolate outside the range of the values that we have actually observed. We can predict values in the probabilities of values in the tail of the distribution, which we've never seen. If we're just using an empirical model, that is, just use the data, our predictions are limited to the range of observed values. And that's fine, but it is limiting. If we're doing simulation, we can use a distribution model, and that's easy, but we can also just sample from the data set. At-risk allows us to do that. We can also communicate by using graphs, using a histogram, rather than expressing the distribution. So we have a choice. But these benefits of having a distribution model do depend upon having the right one. If we're just throwing a model in just because, or why not normal, then maybe we should think about that a little bit, because the wrong model has a penalty attached to it, and it could be worse than using no model at all. Let's talk about some graphs, because the best way to do statistics is visually, I think. And let's look at some graphs that help with this whole process of distribution models. I'm going to show you 4 different types of graphs. And each graph is going to be displaying the same raw data and the same distribution model. And in this case, the distribution model does not fit the data. I have this same data set that I used on an earlier slide and a normal distribution which clearly does not fit the data. So we can see how these graphs allow us to visualize and reject a poorly fitting distribution. Well, this is a histogram. You've all seen this. It's familiar. Pretty much everyone in our world knows what a histogram means. And how does it work as far as testing or evaluating the fit of a distribution? Well, it works fairly well to identify distribution models which obviously don't fit. But if you're trying to find the best fit, then other graph types are a little more effective. Let's look at some of those. Here's a graph which you may or may not have seen, and it's called a CDF plot, or cumulative distribution function plot. This plots the cumulative probabilities of observing values going from low values on the left to high values on the right. So the y-axis goes from 0 on the left to 1 on the right, and the CDF curve always increases. There's 2 curves on this plot. The red curve is based upon the data. It's the empirical CDF, the empirical distribution function. That's kind of a stair-steppy curve because the data comes in discrete chunks. The smooth curve is the model. That's the normal distribution model. And you can see the 2 lines don't track together very well. Later, when we talk about goodness of fit tests, we'll see that several goodness of fit tests are based upon the distance between these 2 lines on the CDF plot. And so this graph, this particular graph, has an important relationship to goodness of fit testing. Now let's talk about this plot. This is a probability plot, or more simply just a probability plot, or in at-risk, it's called a PP plot. Now, this plot is a special plot for each distribution that you're testing. And you notice both the x and the y axes go from 0 to 1. This plot plots the probability of observing values less than a given number as you go from 0 to 1. The horizontal axis is for the it's for the data itself. That's your empirical curve. on the y-axis, the vertical axis, is for the model itself. Now, if you have a good fitting model, the way this curve works is you should have a straight diagonal line right down the diagonal of the plot. And you can see this one is not straight. It's curved. And it tells us, well, this is definitely a bad model. And that's about it for this plot, I think. I did want to mention that the correct pronunciation is PP plot. This is not to be confused with a PP plot. That's the area of my backyard where the dogs like to go. And grass is greener there. I'm not sure why. Let's move on. This is the other kind of plot I wanted to show you. This is a quantile-quantile plot, also called a quantile plot or a QQ plot in at risk. This looks and is interpreted similar to the PP plot. However, seems to curve a different way, and that's because it's constructed a little bit differently. On this plot, again, a straight diagonal line indicates a good fit, and we don't have it here, but it's curved the other way. Both the x and the y-axis are not in terms of probability here. These are in terms of quantiles. These are the values of the data that we're trying to fit a model to. So in this case, our flatness data that I'm fitting has values of 0, 1, and 2, and so forth. But and you can see those are the actual values on the x and the y-axis. So it's a different construction of a plot, but it's interpreted the same way as the probability plot. Perfect fit is a straight diagonal line. So which plot is best? Well, that's a good question, and I would say without a doubt, if you're presenting something, if you're presenting what your fit is or what the best fit is, I'd stick to a histogram. The reason for this is that people understand it. And if you show a graph which your audience has never seen before, and never seen a graph of that type, they will spend a lot of mental energy trying to figure out what it is you're saying with that graph and what that graph means without understanding your point that a particular model fits or doesn't fit. So if you just show a histogram, you kind of convey your point a lot simpler. But it's not, the histogram is not the best way to discover which distribution model fits the data. Studies have shown that diagonal lines are better for this purpose. Diagonal lines, first of all, they're more interesting from a design point of view. The eye naturally goes to diagonal lines faster than other slopes of lines. And other studies have shown, notice I'm being quite vague on that because I can't actually point to them, but I read in a book somewhere that studies have shown that diagonal lines make it more effective, or it's easier for people to detect changes in slope when the line is diagonal than other slopes. As a result, the PP and QQ plots are both designed to take advantage of this aspect of human physiology. And they're more effective for discovering which distribution model fits as a result. But there is a difference between the quantile plot and the probability plot that I want to point out here. Let's go back to the quantile plot, and I want to see if I can get a highlighter going here. All right. The QQ plot here has a lot of points all squished together down in this lower portion of the curve. They're all really close together. And if you look at the upper portion of the curve where there are very few points, see this one straight line way up here, that's the distance between 2 points. So visually, ask yourself, is this a fair representation of the data set? I've got 1 point that is controlling this last section of the plot and a whole bunch of points that are squished down in this bottom end. Is that visually fair, or does it emphasize the tails maybe a bit too much? If we go to the probability plot, this plot has roughly the same distance of curve devoted to each point. And as a result, I claim that this is a more visually fair representation. So for that reason, go the other way. There we go. For that reason, I think the probability plot, or the PEP plot, is the most effective. I just wish they'd chosen some different name, but that's just me. Let's go on. Let's talk about everyone's favorite goodness of fit tests, shall we? And let's talk about how these tests work. Well, goodness of fit tests always start with data. You have to have some data to test. And the first thing you do is to choose a distribution family, like normal, Weibull, gamma, or whatever. We're going to test a family of distributions to see if the data fits that family. The next step is to find the best distribution in that family that fits the data. And if you're using computer software, whether it's at-risk or Minitab or any other software, this is done for you automatically. And my advice is just let it be automatic. Don't worry so much about how it's done, because for many of these families, it's quite complicated. For normal, it's fairly easy, but in general, it may not be so easy. So at this point, we have the best distribution in that family that fits the data. Now what? Now we do the goodness of fit test, and the way we do this is by calculating a goodness of fit test statistic. All of the tests that we're going to talk about are designed so that a larger value of this test statistic indicates a worse fit. So higher value is a bad fit. A smaller value, close to 0, indicates a better fit. Or more precisely, it indicates a less bad fit. Now, optionally, and many programs and people do this, you can look up what's called a p-value in a table. And if you've been around statistics much, you'll know that p-value is kind of the universal way of taking statistical tests or hypothesis tests and distilling it down to a common language for interpretation. The p-value is, in general, is the probability that, I'm going to use that nasty word, null hypothesis. I'd rather just skip that. Here's the way to deal with p-value in a goodness of fit test. If the p-value is small, let's say less than 0.05, then we conclude the distribution does not fit, and we can say with at least 95% confidence that the p-value does not fit. And if it's greater than 0.05, then we can't say it doesn't fit. But what can we say? The issue that I have, the fundamental issue with goodness of fit tests, is they don't really measure goodness of fit. What they measure is badness of fit. They all measure how bad the fit is. And rather oddly, someone decided we should call these goodness of fit tests. And so here we are trying to explain them. Goodness of fit tests are statistical tools designed to do one thing well. Unfortunately, it's not the thing we often want to do. But what it does well is to prove that one selected family of distribution models does not fit the available data. It's kind of negative when you come to think of it. It does not prove and cannot prove that the model does fit. And more importantly, I think for us in the modeling world, it can't tell you which distribution model fits better. It just says, well, this doesn't work. You're on your own then. So what do? Well, the problem is a little compounded, I think, when people rely on p-values a little too much, because we can use a p-value to reject a candidate distribution model, and yet, in practice, I found this can be confusing and distracting. If I have a small data set, let's say 15 or 20 or 50 numbers, it's typical that I could test a whole bunch of different families, and none of them will be rejected. They'll all fit fine according to the goodness of fit test, according to the p-value. But does that mean that they're all okay, that they're all good to use? Not necessarily. And then we have large data sets. If I have 1,000 numbers, any little wiggle, any little bump or oddity with the data set can cause all of those distribution families to be rejected. They're all bad. Then what? Then what do we do? So the p-value, I think, adds confusion to this, and I would rather just ignore it. What we really need here is a procedure that tells us which of several distribution families is best. Now we can twist this goodness of fit test and try to make it work for this by doing it this way. We run goodness of fit tests on several distributions, which we choose because they might fit, and compare the test statistics. Ignore the p-values for now. The lowest test statistic, or the one closest to zero, usually indicates the model that fits best. Now let's talk about some types of goodness of fit test. And the most popular, maybe original type of goodness of fit test, been around for 100 years or so since Pearson started using this, is the chi-squared test. The chi-squared test makes a kind of a histogram in the computer and compares the heights of each bar to the distribution model. And in these pictures, I have a histogram and I have a red outline of a model histogram on top of the histogram. And you can see that on the left panel there, that the red line is closer to the blue data. But on the right, it's pretty far away. And the chi-squared test literally measures the distance between this red model and the blue data. And if that's too much, it says, nope, this doesn't fit. We reject it. Now, it's a little more complicated than this because the histograms which work best for a chi-squared test are not the same histograms that we would use to visualize the data. The histograms for chi-squared tests are usually constructed so that each bar has more or less equal probability of observing values in that bar according to the model. So the bars are not of the same width. That's pretty hard to visualize, but the computer, if it's programmed right, usually takes care of this. An advantage of this tool is that it works for both discrete and continuous distributions, and you'll see some of the others do not work for discretes. The disadvantage, in my mind, is that if I choose a different histogram, if I choose different bins, more bins, fewer bins, equal width bins, or equal probability bins, then the result may change. The model which fits best may be different. And that's really annoying to me, that there's no unique answer to this chi-squared test. It annoys me anyway. I don't know about you. Let's talk about another one. And the other major family of goodness of fit tests are called empirical CDF tests. Again, CDF is a cumulative distribution function. These tests are all based around the idea that the cumulative probability of the data, that's the empirical CDF, will track closely along the model CDF if the model fits the data. And the picture on the left shows a stair-steppy empirical CDF and a model that fits nicely. On the right, I have a model that doesn't fit, and you see the lines don't track. So the biggest distance between these two lines is a reasonable indicator of the lack of fit of this model. Now, an advantage of this technique is that it provides a unique answer. It does not depend upon how you construct a histogram. So from that point of view, I like it better. But a disadvantage is that this only works for continuous distributions. We haven't, or people haven't generally accepted a method of using this for discretes yet. Now, there are several named tests that are all empirical CDF tests. Let's see what's different about these tests. The first empirical CDF test, I believe, was the venerable Kolmogorov-Smirnov test. And this is called KS test in at-risk, and it's in a variety of other software products as well. Now, one fact about this test is that it tends to be more sensitive to the shape in the middle of the distribution and less sensitive in the tails. What do I mean by that? Let me go back to this slide. Over here on the left of this data, I have a lot of data points here. If I have some lack of fit of the data, in this area, it's going to create a large distance between these two curves. But over here in the tail, a lack of fit will not create so much of a distance. As a result, this Kolmogorov-Smirnov test is going to be much more is going to find a model that fits much closer in this fat section or the middle section. In this case, it's not middle. Let me say the high probability section of the distribution rather than in the tails. Now, maybe that's an advantage in some case. I don't know. There's another test which is in StatTools, another Palisade product, called the Lily Force test. And I had to look this one up because I'd never used it before, but I just wanted to let you know because it's in there. Now, this test is an adjusted version of the KS test, which works for the normal distribution only. And it's actually more effective than the KS test in rejecting non-normal data. So if your goal is to prove that a data set is not normal, and you can just stop there, then the Lily Force test is probably a good tool. But if you actually want to find a model to use, then it doesn't really help you much because that doesn't work for other distributions. Let's talk about the Anderson-Darling test. This is called the AD test in at-risk and in other software tools as well. This is another adjusted version of the KS test, and it's designed to more fairly test the fit in the tails and the middle of the distribution. In effect, it has some weighting factors which tend to weight each point on the each point in your data set more or less equally. So as a result, the Anderson-Darling test can be used to test different distribution families to compare them, and the lowest AD test statistic indicates the least bad fit. You can decide if it's the best fit. And for my money, this is the best all-around goodness of fit test. And so in general, this is what I recommend. Let's talk about the process of fitting continuous distribution models in at-risk. And we just talked about a bunch of stat geeky tools, right? Graphs and goodness of fit tests and confusing stuff like that. You know, the most effective tool has to be that gray matter between your ears. It just has to be, because if you're not thinking about what is behind this data, what is it that's actually generating the data, then you're missing a lot. You may know more than you think about what is behind the data, and that may help you to select a distribution model that is more appropriate. The more we can combine our knowledge of what the system is and what the system isn't into this process of selecting a distribution model, the better off we'll be. If we just plug the data in the computer and let the computer churn and say, well, this is a 3-parameter whamma-gamma distribution, and we say, okay, I'll take that, you're really not, you're selling yourself short, because I think you know more than you think you do about what you're thinking about. Boy, that really sounded bad. Let me move on here. I'm getting highlighters. Come on, go back. Hello. There. Fitting continuous distributions. So which distribution family is best? Here's some things to think about. Some thinking questions. And before I just go there. Ask yourself, what do you know about the origin of the data? What theories and facts do you have about the system? Has there been any other attempts to fit distribution models to this data in the past? Do you have any expert opinion to consider? Is there a story behind the data which is consistent with one family of distributions? Now, as you learn more about different distribution families, you'll find that each one was basically invented because of a different story. There were stories that led to Weibull and stories that led to Rayleigh and Gamma and so forth. And the more you learn about those stories, the more you can start to recognize these situations when you come across them in real life. Perhaps the most important thing, or the most common thing, let me put it that way, that people realize is that there are natural boundaries on the upper and or lower tails of the distribution. And if the boundary is near to the data, this is going to have a strong impact on the shape of the distribution. So if the boundary is near, and I would say within a few standard deviations of the mean, then we want to consider only models that have that bound built in. But if the boundary is far away, more than a few standard deviations, then consider both bounded and unbounded models, because whether you have a bound or not isn't going to make that much of a difference. I'll give you some examples, and let's see how this works. Now, in at risk, there is a distribution fitting menu, and that distribution fitting menu comes up with a form, and in the distributions to fit tab of that form, do I still have my highlight? Click on distributions to fit, and then you get this very useful form. And I like this in particular because it helps us make use of what we know and what we don't know. If you know stuff about the lower limit, if you know that it's fixed at a certain value, or bounded but unknown, or open, that is extending to minus infinity, or you just don't know, you click the appropriate buttons there, and the choices of distributions change depending upon your selections. So it is a convenient way to limit your choices to distributions which are appropriate. Now, you have the choice to either specify the boundary value if you know it from the process, and that's what I'd recommend, or just allow at risk to estimate it for you. There are a wide variety of distribution models in at risk, and I've organized them. These are continuous distribution models. I've organized them in a table here for you based upon whether they're bounded on the left or on the right or unbounded. In the middle top cell of this table, where it says bounded left and right, these are distribution models that have an upper and lower bound, and we have three of them, uniform, triangular, and beta. And the beta actually has a variety of shapes, which includes some triangulars and uniforms and some bimodals, and it's a pretty flexible distribution if you have upper and lower bounds. In the top right cell of this table are left-bounded distributions. And this happens so much that there are a large variety of these distributions out there, and way more even than are listed here. But with this family of distributions here, these 9 different families, you can find a pretty good fit for almost any left-bounded situation. On the bottom right cell of this table are the unbounded distributions. We have our venerable normal or Gaussian distribution. We have the extreme value distribution. Now, I should mention this is there are actually 2 versions of this extreme value. There's a smallest extreme value and a largest extreme value, and if I say which one this is, I'll probably get it wrong. I've got to look that one up. But if you can turn the data around just by entering the negative of the data and fitting it, and the opposite extreme value might fit that as well. So I just mentioned there's 2 families there, logistic and student. So there are many choices here. Now, what if your data has a bound on the right, an upper bound, but no lower bound? We have an empty cell in this table. And that doesn't come up that often, but it does happen. So what do? You simply take the negative of the data and then fit left-bounded distributions to the negative of the data. So that's a problem easily addressed. Yeah. Next. Let's take an example. And I think I'm going to attempt to go to Excel here. And, oh, by the way, I should mention that the reason why I was late is I was scurrying around to create a website that contains these files for you. And if I can do this, I'll show that to you. If you want to download these files to play with them yourself, you're welcome to go to this website, which is andysleeper.com/whybenormal.html. And I'll give that to you again at the end if you like. But here, you should be able to download the PowerPoint slides as a PDF file and the 4 data sets that I'm using. Now, I've had some trouble putting this up, so if the links don't work, tell me, because I didn't have a chance to test them. Let's get back to business. Here are some measurements of flatness of something. Well, what do we know about this? Not much. We do know that we have 70 observed values. It's always positive, and we have no history of distribution models. So let's use left-bounded distribution models, and let's see what we can fit to this data. Using at risk, I'll go to this distribution fitting button and fit distributions to data. And an important thing to select is this is continuous sample data, so I want to click that. Distributions to fit. What's the lower limit? So I'm going to give it a fixed lower bound of 0 and an upper limit of open, extending to infinity. So I have these lower bounded distributions. Now I'll say fit. And it comes up with something. Now, an important, it comes up with a suggestion of a distribution, which happens to be the exponential distribution. How do I know that? Because it says up here at the top, risk expon, and it has a number. And over here in the table on the left, it put the expon distribution on top. These are ranked, however, according to the chi-squared test. I don't particularly like that, so I'm going to switch it over to the Anderson-Darling test. And gosh, the best test, best model changed, didn't it? Now I have a Weibull distribution as the top, followed by gamma. That's interesting. I wonder what happens on the Kolmogorov-Smirnov test. Well, now I have exponential again, and followed by gamma and Weibull. You know, if you look at all of these numbers in the table, these all represent the badness of fit, and they're all pretty darn close. So it's as if Weibull and gamma and exponential are all really, really close to each other. And in fact, they are. The fact is that exponential is actually a special case of gamma and Weibull. So if exponential fits, so will gamma, and so will Weibull. You don't have to know that, but it helps. I've gone through this. I showed you that. So which model should we use? We've got 3 candidates, Weibull, gamma, or exponential. For simulation, you know, any of these models will probably work fine. But I like the exponential model because it's simpler. It only has one parameter. You can see up here in the risk Excel functions that there's only one number. So the exponential is a simpler distribution, and so I'm going to prefer that. It's almost as good as the others. Let me go to the next slide. Oh, here's another example. This is plastic hinges. We've all seen these little plastic hinges on little boxes, and they're designed to work until you consume all the contents and then not to work anymore. So how many cycles does it take before a plastic hinge fails? Well, let's say we took 55 of a certain hinge and we tested them in a little bending machine until failure and counted the cycles until it fails. Which model is going to fit this data best? Well, what do we know about this? Well, I have 55 observed values. All the units failed during the test. And if you know reliability analysis, this is a complete data set, not censored at all. Censored data we're not going to be able to fit. And at risk, we would have to go to a reliability program to do that. But if it's a complete data set, then we can fit it in at risk. Let's say we ask a reliability engineer and says, well, Weibull's always worked for me. So based upon that, he suggests Weibull. Why not? Clearly, all the values of cycles to failure must be positive, but is 0 a meaningful boundary here? Let's look at this histogram. The lowest bar on the histogram is 840, and the highest bar is 1300. Sure, they all have to be positive, but 0 is a long way away. So the boundary in this case doesn't really matter, and therefore I'm just going to say unsure for the lower and upper limit. And let's see what happens. I think at this point I can go to Excel, and I should have that file open here somewhere. Unsure. Fit. What does it suggest? Well, by this criteria, the reliability engineer would be happy. It likes Weibull. Well, just for the grins, let's check chi-squared. That's interesting. Chi-squared likes this beta distribution. And the Kolmogorov-Smirnov also likes beta. Well, now what do we do? If we're back to Anderson-Darling, we've got this Weibull distribution. So we have a choice to make. And I've already shown you that. Choices, I would say, the two good choices are Weibull and beta general. The Weibull is best by Anderson-Darling, but not by the others. Now, according to this model, at risk put in a risk shift, which you can see here. And that means that 476 is the absolute minimum cycles to failure, and there is no maximum. That means that it's impossible by this model to have a hinge fail with fewer than 476 cycles. Now, is this reasonable? I can't tell you that. But if that lower bound is reasonable, then that's probably a good model to choose. The beta model has a lower bound of 700, and it also has an upper bound of 1400. So by this model, you're never going to get a failure less than 700, and you're never going to get a failure at more than 1400. Is that reasonable? You've got to ask yourself that. Now, all things considered, I prefer Weibull because I like the Anderson-Darling test statistic best. And the Anderson-Darling test statistic is designed to fit better in the tails, and that's where I believe it matters most. We're trying to predict probabilities of failure in the tails. We don't want anyone to have a failure, a premature failure of a hinge. So we're trying to predict tail probabilities, and that's where the fit is going to be most important for us. Because of that, the Anderson-Darling test is best, and the Weibull model is best. All righty then. Let's look at another data set. How are we doing on time? Not so good. This is the minutes between eruptions of the so-called Old Faithful geyser. I have 299 observations of this data, and what do we know about this thing? Well, I don't have a clue. I'm not a geyserologist. I'm not even a geyserophiliac very much, but I do know that there are people who study such things, and you might see some of these people in this picture here, and so you could go talk to them. Maybe they can help. So we really have no idea. Now, this histogram clearly shows that there's a reason why they didn't call it Old Gaussian. I even think faithful is kind of a stretch, but maybe that's just me. What do we do with this? I would say, here's the case that you go without a distribution model. If you have to have an input like this, and in this case, it's a stable process. It's been behaving like this forever, and we're not going to normalize it. We're not going to manage it and control it. It just is what it is. So we just accept it. And so none of the available off-the-shelf distribution families are going to fit this bimodal distribution. We've got options, though. With at-risk, if you're using at-risk for modeling, you can simply randomly sample numbers from the data set itself with the risk resample function. Or you could splice together two distributions with the risk splice function. Now, that's kind of tricky, but you can do that. Or you could specify probabilities to match histogram bars using the risk histogram function, curiously without the A. Or you could even use a distribution artist to draw your own custom distribution. How about that? So there are options here, but I would not use a distribution model for a data set that looks like this. Now, before I go to discrete, let me just mention that on this desert island question that I threw out at the beginning, I like the exponential distribution. If I could only use one distribution forever, I think the exponential is basic. It's kind of like a fundamental molecule. You can transform the exponential into a wide variety of other shapes. So I think it's pretty useful, and it's also quite fundamental in physics. It matches a lot of natural processes like radioactive decay and a lot of other things as well. So it's pretty handy. Let's move on to discrete, though, and I'll be quick here. Fitting discrete distributions is a little different from continuous for some not so obvious reasons. In most cases, of course, discrete distributions are used to represent counts of events, and they're limited to integers like 0, 1, 2, etc. And we have only one goodness of fit test that we use. That's the chi-squared test, the one that I don't like. But that's what we got. The empirical CDF tests are just not available. Also, the QQ plot is unavailable, but at risk will produce either histograms or PP plots, so that's fine. Often, you just think about the process and think about the stories associated with discrete distributions, and that may be enough to select the most appropriate distribution family simply by theory. Let me show you what I mean. Here's a distribution that is really very popular for a lot of situations. It's called the Poisson distribution. It's a simple family with only one parameter, lambda. That's the mean of the distribution. And, of course, this graph doesn't look too simple because I've tried to show 6 different Poisson distributions all in one graph, which makes it kind of cluttered. But the idea is this. When events occur, random events occur independently, counts of events per unit of time or counts of events per unit of space or product often have a Poisson distribution. So it could be like number of products failed per day, number of phone calls received by your call center, or the number of lottery tickets you have to buy before you win. Actually, that's another distribution. I'll get to that in a minute. But this model comes up so much that the Poisson distribution can also be called the Per distribution. It has a nice feature that if you add Poisson distributions up, you get another Poisson. So it's very convenient. The simplest of all distribution models is the Bernoulli distribution. It only has 2 values, 0 and 1, and think of it as like flipping a coin. It's 1 if it's heads or 0 if it's tails, except it could be an unfair coin. It could specify any probability of getting a 1. This is a simple model for any event that may or may not happen, like someone will buy or not buy, you win or lose, you fail or you don't fail. And at risk, this is so simple that it's not even in at risk, but you can model this with the binomial function with the first parameter being 1, because Bernoulli is a special case of binomial. Here's another distribution I wouldn't mind having on my desert island, although the underlying question is, would it get me something to eat? But in any event, with this Bernoulli distribution, I could actually build a variety of other distributions. If you think of the Bernoulli distribution as an output of a 2-outcome game, where P is a probability of winning the game. And when I say game, it could be any experiment with 2 outcomes. And we have to assume that all the games are independent of each other. And winning the game could be a customer who buys, a product which fails, any number of things. Then we can derive a lot of different distribution families based upon this Bernoulli model. The number of wins per one game is a Bernoulli distribution. The number of wins per n games is a binomial distribution. So if I flip a coin 10 times, how many heads do I get? That's binomial. The number of losses before the first win has a geometric distribution. So how many times do I flip a coin before I get my first heads? That's a geometric. How many lottery tickets do I have to buy before my first big win? That's also geometric with a much different probability. The number of losses before the S win is a negative binomial. So how many times do I have to flip the coin before I get 2 heads or 3 heads? That's binomial. Confused yet? Yeah, me too. Let's look at an example. Let's say we're trying to plan a production line, and the automated final tester diverts failed units into some kind of repair queue. And let's say that we're planning on up to 2% of the units failing this test, which would not be so good, but let's say we want to prepare for that. If 2% of the units fail, here's the question. In a pallet of 144 units, how many units will fail the final test per pallet? Well, if you want to simulate that, it has a binomial distribution with n equals 144 and p of 0.02. Maybe you'd like to know how many units will pass between failed units. Well, that's a geometric distribution. And suppose we want to make sure that the repair queue is big enough. Let's say that it will fill up if it contains more than 4 units. So how many units will pass before the 5th failed unit, causing the repair queue to overflow? Well, that has a negative binomial distribution. So with that simple idea of a pass-fail game, a win-loss game, or a binomial, or a Bernoulli experiment, with that simple idea, we can build a wide variety of complex and often useful discrete models. That's what I recommend often for fitting discrete models. Now, with that risk, you can also use the chi-squared test. And let's see an example. Okay, some guy named Noah has been around counting the number of hurricanes that have affected the U.S. each year. And I have a table of Noah's data. Now, before we go off fitting a distribution model, a good initial question is, does this data represent a stable process? Are we getting more hurricanes every year or fewer? Is it really stable? Now, without doing a fancy test on this, you can sort of make a visual assessment that at least over the last 150 years, I would say that, yeah, it looks pretty stable. So what distribution model would we use to fit to this data? Well, let me go back to at risk and let's check this out. Here's my hurricane data. I go to at risk and distribution fitting. Okay. Now, I have selected, and this is important, this is discrete sample data, so it's going to change the options just a bit. If I go to the distributions to fit, now I don't have these options anymore as far as a lower limit or upper limit, but it's picked a variety of discrete distributions. And I say fit, and it goes away. Oh, that's not a very nice plot. Let's go to, there we go. Let's go to a plot like that. This shows us the discrete distributions, and the blue represents the data, and the red represents the model. So in this case, well, I have chi-squared, and that's my only choice here, so I guess I'll live with it. The chi-squared distribution says that the negative binomial fits best. But I want to check something here. If I go back to this distribution fitting, and I look at this chi-squared binning tab, here I can choose different algorithms for how that virtual histogram inside the computer is constructed. How are those bins constructed? Well, I can choose equal intervals, which means bins of equal width, or I could choose equal probabilities, which is actually the default. Now, let's click Fit. I get a warning that says that with discrete distributions, you can't quite get equal probabilities, but I'm okay with that. It'll do close. Now, with equal probabilities, the best fitting distribution is Poisson, and negative binomial has gone down to 3rd place. I'm just showing you this to illustrate that the way the algorithm is performed can sometimes change the distribution that your chi-squared test will recommend. And that, at the moment, is just a fact of life. I don't have a better tool to offer. So a recommendation for direct fitting is to change this algorithm to equal intervals. Now, maybe it's not going to work in all cases, but I think at least you'll get a more representative model. Now, okay, here's just an illustration of the best fitting distribution changing from Poisson to negative binomial, depending upon that chi-squared algorithm. And boy, I think I'm done. It's just time for some shameless self-promotion. I have this book out, which is called Six Sigma Distribution Modeling. It talks about dozens of distribution families with application examples, graphs, and formulas, and information about non-normal control charts, capability metrics, a glossary, and so much more. And I'm offering a price that's so good I can't even utter it here. So call me or email me if you'd like to get a hold of my book. With that, I think I will try to find a way to pass this back, see if either of our listeners have any questions.
Oh, let's leave this book up because people may be watching this recording later, and you can email me, jromeo-kall@palisade.com, and I'll help you out too if you need to get a hold of Andy.
Excellent.
And also, I just wanted to say to everybody, we are going to send a link out to this recording, and I'll send a link to Andy's website too with the files.
Where'd that website go?
But yes, it's time for some questions. If anybody has any questions, feel free to ask them now.
Questions come in on chat, or do you read them off?
They can just type it in on chat. I do have one question already.
Okay.
While selecting a triangular distribution, can we assign weight so we get data skewed to one end?
When selecting a triangular distribution, I'm not sure I understand that. If you're selecting does that mean if you're fitting a distribution to data, if you're using the fitting algorithm in at risk, it will actually choose the weight. Well, it won't actually weight. It'll simply find the best fitting triangular distribution, which may be symmetric or maybe not symmetric. It will just find the distribution that fits the data best. You obviously have the option to modify that model after it's fit, but that's and there is one point I wanted to make. The goodness of fit test statistic that you choose has nothing to do with the fitting algorithm. It has nothing to do with selecting the best. Boy, that was confusing. Remember at the beginning of this presentation, I said you fit the distribution model first, then you calculate the goodness of fit test. The particular triangular distribution that at risk will recommend is not related to whether you choose chi-squared or Anderson-Darling. So I think you just use at risk to fit the best fitting triangular distribution, and if you need to modify it for some purpose, then you decide to do that. I hope that's helpful. If not, feel free to ask another question.
Oh, let's see. We'll wait just a second. I do see some messages in the chat that said, "Thanks, Andy. Nice job, Andy. Thank you." So
all right, that's good.
Good shape.
You're very welcome. Thank you for being here.
My consensus is the same. This is an excellent webcast, and we really appreciate you doing it. Let me see if I have any more questions. When I was doing a project, I was using at risk. All the time when I was trying to see the best distribution fit, the result I got the most was beta general distribution. Why was this?
Without knowing your data, I can't say. I can only speculate. I will say that the beta general distribution is a very flexible family because it has the upper and lower bounds that can be anywhere, and it has such a wide variety of shapes. It can look like a bell-shaped normal distribution. It can look like triangular. It can look like uniform. It can look like exponential, except it has an upper bound. So I think, this is pure speculation, that the beta general can handle so many shapes that if you're just picking a lot of real data sets out there, it has a better chance of fitting it. Whereas other distribution shapes like normal always has the same shape. So if it's not that nice bell shape, normal's just not going to fit. So that may be quite a natural response to the fact that beta is such a general distribution family.
Good. I bet you that answers it.
Hope so.
And I think we're going to have a lot of questions, and feel free to forward them to me or Andy. We'd love to answer them. I think we do have quite a few distribution questions. I think I'll probably just have time for 2 more, and I think because we do have a lot. I just want to say again that yes, we will have a link to this, and I'll send that out to everybody. Now here's what if I would like to have I'm sorry, I can't pronounce this, Frechette rather than a Weibull distribution. That's a F-R-E.
Frechet.
Frechet.
Frechet. I've heard of it, at least. Frechet distribution comes up in extreme value theory, where the extreme value theory is about what happens when you have a distribution representing the biggest of many things or the smallest of many things, and depending upon the nature of the individual distribution, there are only 3 distributions which define the how to avoid using too big words here. There are 3 asymptotic distributions which fit the largest of many things or the smallest of many things. One of them is Weibull. One of them is the extreme value or Gumbel distribution, and the third is Frechet. Now, that distribution is very seldom seen. I would have to say that I've never seen a real case where that fits, but I would also say that I've never been able to test that distribution because it's not built into, well, I can think of one software where it's built in, but not this one. It does come up rarely, but it does come up. And so I can't give you a complete answer as far as how to test that distribution because it's probably not so easy. However, I will say that Chapter 12 of my book does talk about it, does have the formula. Good. And so the information is out there if you want, and I can look into it further if you have a specific need or application.
Oh, great. Maybe just one more question, but I'll read this off. How does at-risk fit the distribution to the data without reference to the goodness of fit test? What criteria does it use to pick distribution parameters?
Excellent question. And
yes.
I can answer that in general. However, I'm not privy to all the details of at-risk.
We'll get the team on it.
Yeah, but let me give you an example. Suppose I want to do a test a normal distribution to see if normal fits. Well, how do you know which normal? Well, you estimate the mean. The best estimate of the mean is to sum up the data and divide by n. The best estimate of the standard deviation is the usual formula for standard deviation. It's STDEV in Excel. So with that mean and that standard deviation, we have selected the best normal distribution without doing anything relating to goodness of fit. That's just the best of the normal family. Now, does that fit the data? Doesn't tell us. We have to do a normality test to see if that normal distribution really actually fits. Now, as far as your question about how at-risk selects the data, or selects the best parameters for the distribution model in that family, I believe it is maximum likelihood estimation, which is a general tool we use to estimate parameters for any family. It's the easiest and most reliable way to do that, but at-risk may or may not be using that in a specific case. So I think I have to leave it there as far as that goes. But the estimation of parameters does happen as a first step before you go into calculating the goodness of fit test statistic.
I think that answered it. Thank you.
You know, I've taken my way
so
through
much.
it.
And Andy, this was great. I think
Good.
we better let you go, though.
Okay.
But
well, I'm happy that I was able to share a few ideas and things. And like I say, feel free to contact me, and I can be happy to follow up with you personally if you are interested.
Thank you, everybody, for coming. And once again, I know we have a lot more questions. Feel free to contact us about them. And this will wrap up this session. And once again, thanks.
I think I just passed the ball back to you, didn't I?
Yeah, I've got it.
You got it. Good. All right.
Hey,
Thank you, everybody, and I'll talk to you soon, I hope. Right. Bye-bye.